Okay, so we are going to talk about centripetal acceleration today, and we'll go to the visualizer to start off with. So there's three things we need to be able to do by the end of the lesson. The first is to explain why velocity is not constant when traveling uniformly in a circle. Okay, so we're going to explain why velocity, and the key word there is velocity, is not constant when traveling uniformly in a circle. So, for example, this could be like the Dragon spacecraft orbiting the Earth last week, or the ISS now orbiting the Earth. So they are traveling uniformly, so they're moving around at the same rate, but the velocity is not constant, and we'll come back to that in a moment. We're going to determine the direction of any acceleration, because we know if we don't have a constant velocity, we are going to have an acceleration. So the direction of acceleration. And we'll then link that to some ideas about it. And finally, we're going to calculate the centripetal force acting on our object that is rotating. Okay, so we'll get rid of those, but let's start with our idea of what's going on. Let me just do that one. Okay, so we've got an object that's moving in a circle. It's moving round in a circle and sort of transcribing that circle. Then it can have a constant velocity because it can rotate round at a constant rate. So the time period for rotation can be constant. But we know that if it is going round in a circle, then at every stage in that circle, its velocity is changing because that velocity acts tangentially, which means sort of at right angles to the circle, at that point as it's going round. So let's draw ourselves a diagram to sort of try and make sense of this. So there's our centre of our circle. And you have to excuse how bad the circle's going to be on here because it's not great on our whiteboard. But there's our circle that we're transcribing. Now, if we consider that an object, let's say, starts at this point here and moves to this point here, then its speed might be constant. Because speed, remember, is a scalar, not a vector. So the length of these arrows would be exactly the same, seeing as they are our magnitudes of our velocities, but the direction has changed. So as our object moves around this circle, as it's transcribing this route around our centre of the circle, the velocities are changing direction. Okay, but the size of those velocities, the magnitude of those velocities remain the same. So we've got to remember that velocity is a vector, which means it has both size and direction. In fact, better to call it magnitude, but we'll go simple here. Size and direction. And if we're changing direction, then we are changing the velocity, but the speed remains the same. Okay. So why is that important? Well, it's important because we know that a change of velocity over a change in time is in fact an acceleration. So even though our magnitude doesn't change, our size of our velocity doesn't change as it's moving round, the direction does. So there must be an acceleration causing that velocity to change as it moves round the circle. So because that velocity is constantly changing, there must be an acceleration. Now, we can kind of understand what that acceleration is. If I get rid of this circle now, and we draw on two arrows that we were just looking at, so they should be the same length. Oops, that's a bit big, but anyway, they should be the same length because the magnitude remains constant. So the size, so my speed is still the same. But if we now overlay them at the same point, we'll see that there is a different, in fact, let's colour it green. There's a different vector here, vector between the two, which is in fact our acceleration. So you might notice that this acceleration is actually acting towards the centre of the circle. Now I want to show you this slightly better by using the PowerPoint slide. So give me 1 second. Let's shift to PowerPoint. So here you can see the circle, and we can see velocity A and velocity B. So velocity A is tangential at this point A, and velocity B is tangential at this point B. So we've got those velocities, and the sizes, the magnitudes of those velocities are constant. It's only the direction that's changed as you're going around the circle. So if we then overlay the two, as you can see here, we've got this extra vector quantity, which is going to be our acceleration, because that is the change in velocity A, or change in velocity, sorry, VB minus VA, divided by time, which gives us acceleration. And if we go a step further, and I have to do this by going back to the animation, let me just group those. Sorry, I should have done that earlier. So if we go back to this here, and we overlay it, you can see that at the point B, that acceleration vector is acting down the radius of the circle towards the centre. So wherever we take it, that acceleration is going to act towards the centre of the circle. And that's really, really important. So the acceleration, oops, choose the right colour. So the centripetal acceleration acts towards the centre of the circle, or the sort of circular route that it's transcribing as it moves round. Okay, so let's do the proof. Let's do a proof of what this acceleration actually equals and how we get to it. So as I've said, you don't need to know this proof, but this proof should help you understand it, and certainly this is some quite good physics and some quite good maths to go with it. So let's consider, let's go back to red again. Let's consider two velocity vectors, which are there, and we'll consider an angle as well between the two, and we're going to call that angle delta theta. Okay, so a small, in fact, let's draw it a bit bigger for you. So delta and a theta. Okay, so a partial differential, if you've come across those in maths, which you probably won't have done quite yet. And so as those velocities link together, we have got our acceleration. So in this case, we would be going round a circle with a point over here somewhere. So it'd be going round in a circle. Let's try and draw this a bit better for you so you can see. So there's the circle we're going round. Let's use the blue. I'm going to use that, yeah, so I'm not confusing you. So the blue here is our two radii. This angle here is also d theta, because you have to think if you start here and you're moving to here, you're still moving through that same angle. And then we have got our two velocity, oh, that is terrible, sorry, I'm not leaving that. Two velocity vectors at those points. So one going off in that direction and one going off a little bit in that direction. Okay, so this is sort of that bit, but I've moved those arrows around. Let's make it that way so it's a little bit easier to see. Okay, so we've got that acceleration. It's acting towards the centre. In fact, I'm going to get rid of that because I think I'll confuse you if I stick with that. So we'll go for one at that direction, one at that direction, and then there is our acceleration. Okay, so we've got those two velocities acting at those points, and we're going to name those points as well. So we'll name it A, B, and C. Okay, so the distance they move, this distance here between A and B, so we'll put AB distance, we'll call it a change in displacement, delta S, is in fact going to be equal to the velocity that they're moving at multiplied by the change in time. So the change in the distance they move, changing their displacement from that point to that point, is going to be equal to their velocity multiplied by the displacement of time at that point. Now, we also know that this value A, we could call the change in velocity, so little delta V, which would be equal to velocity B minus velocity A. And that would give us this idea here, because again, remember this is velocity A and this is velocity B. Okay, so it's important to note that these two triangles are pretty much exactly the same. In fact, they have exactly the same shape when that's d theta. They have exactly the same shape because those velocity vectors are moving by a same angle as the angle we have in this quadrant here. And over here, you can see they're moving by that same angle as well. And you kind of have to prove that to yourself by doing a scale drawing to check it, but it is true. So the triangle ABC and the velocity vector triangle have the same shape because the sides are equal and delta theta is also equal. So triangle ABC and velocity vector triangle have same sides equal with delta theta angle between them. Okay, so now let's go and do the kind of complicated bit, the idea we're going for something a bit more complex. So let's now imagine, as I've always said, we physicists, we like to see what the limits are. So if delta theta tends towards 0, what's going to happen? Well, if delta theta tends towards 0, then what we can say is that the change in my velocity divided by my velocity is going to be equal to the change in my displacement divided by my radius. Okay, and you kind of have to prove it to yourself why that is. I'm going to get rid of this little diagram here. I'm going to get rid of this bit up here, and we'll go to the top so that you can see. And because we know, so those 3 dots are because. So because we know that the change in displacement is equal to the velocity multiplied by the change in time, then we can go a step further with this and we can say, well, the change in velocity over the velocity is going to be equal to, so we're going to take the delta S here and we're going to use V delta T instead. So V delta T divided by R. Now we can clear this up because this is not a very nice equation so far. So let's try and clear it up. Because we know that acceleration is going to be dv by dt. So the change in velocity divided by the change in time. We can therefore say, let's rearrange this so we end up with dv dt. So I've got dv over dt, so I'm bringing that one under, so that means that's got to go up. It's going to give me v squared divided by r, and we know that dv dt is a, So my centripetal acceleration is going to be v squared divided by r. So an important equation to know that we can work out centripetal acceleration, let me just change that to a v because that looked like a u for a moment, is going to be v squared divided by r. Okay, so that's our first equation of the day. Proper v, there you go. Now we can also use some of the information we had from last time, because hopefully you remember that angular speed, omega, is going to be equal to 2 pi divided by the total time period, which is also 2 pi f from last lesson. And hopefully you can also understand then that v is equal to omega times r. And that's an important one, so go back and check that one if you haven't understood it. So we've got v being omega r. Now what we can say is that if I've got v squared over r, then I can say, well, my acceleration is then equal to omega r all squared divided by r, which is going to leave me with omega squared r squared over r, which is omega squared r. So often you can see it as v squared over r, but other times you can see it as omega squared times r. So that's another kind of equation that we get from this. So that gives us what centripetal acceleration is. Because of the fact we've got that object moving around in a circle, its direction is changing, and that change of direction is always towards the centre of the circle, hence it keeps it in that circle. We have got a centripetal acceleration moving that velocity vector towards the centre of the circle. And we can now work it out because we know that a is equal to v squared over r, or we know that a is equal to omega squared times r. So two very important equations, and we'll use those a little bit later on, or you'll use them when you do some questions in a little bit. Okay, so what causes this centripetal acceleration? What causes this centripetal motion? Well, we know from Newton's first law that an object travels in straight lines unless an external force acts upon it. So the Voyager that we sent out to the edge of the solar system will carry on. That's a terrible diagram, but anyway, I don't think it's got solar panels, but you can ignore me for that. But anyway, that will carry on in a straight line unless something else hits it. So unless we've got a meteorite that hits it, or we have another external force, that will not change direction. So Newton's first law tells us that object will continue in a straight line until we have an external force upon it. So let's consider what we've talked about it. Well, we've talked about this idea that things move around in a circle and they're changing direction. So the implication must be that there is a centripetal force causing it to change direction. So as the object in uniform circular motion changes direction, then there must be a centripetal force applied. Now, what does centripetal mean? Because I suppose that's quite important for us right now. Well, centripetal actually means towards the centre. So this is a force that acts towards the centre of our circular motion. And that makes sense because the acceleration is towards the centre of the circle. And we know that Newton's second law, and we'll come back to this one a little bit later on, but Newton's second law is F equals ma. So if we have an acceleration and we have a mass, then we must have a force acting in that same direction. So we'll use that in a moment. But let's talk about what these forces could be. So if we were in the classroom right now, we would be doing, well, you'd be doing an experiment. I don't like this one because it hurts when it goes wrong. But you'd be doing an experiment where you're holding the top of this piece of rope, a piece of glass with the rope through it. We put a mass on the bottom. So we've got a value of mg pulling down. And you've got a rubber bung at the end. And you would be swinging it around your head, keeping it at a 0 angle to the horizontal, basically. And so it would be whizzing around like that. Sort of like that. All the way around in a circle as you move it backwards and forwards. So what would be the centripetal force in this case? Well, the force that's pulling that rubber bung back in towards the centre, that's not going off in a straight line. So if you cut this cord, it would go off in a straight line in the tangential direction, just like we've seen on those previous diagrams. But because it's not going in a straight line, it's going in a curve, the force must be this force here, which we know from our mechanics in the first year of work is our tension. So the tension here is what is keeping this rubber bung moving round in a circle around this pivot point in the centre. So our centripetal force here is tension. Okay, so let's do another example. So here's the Earth. Be over the North Pole. And then maybe use UK. So we have got, or we did have last week, we had the Dragon module. It's a little bit like that. Moving around the Earth. Once it was into orbit, it would move around the Earth with a centripetal, with a circular motion, uniform circular motion, unless it was firing its thrusters. So what force is it that's then keeping that Dragon module from not flying off in a straight line, from carrying on round in that circle, because it's changing velocity at each stage, it's changing direction, the speed might not be changing, but the direction of the velocity is. Well, the force this time is going to be the force between the Earth and the module. So it is the gravitational force between Dragon and the Earth. And that is what will keep it in orbit. And you'll come across how to calculate that later on in the year 13 work, because we'll do gravitational fields. Let's look at, I think I've got 2 more examples that we want to look at, because you need to see sort of everything that you could be asked. So let's consider the London Eye for a moment. They love the London Eye because it's quite a complex Ferris wheel, basically. It's exactly the same as a Ferris wheel. So here is the London Eye, and it has these little pods on it, and these little pods are moving round, and they rotate as well, but we're not worried about that. We just care about what is keeping those pods held on so that they go round in a circle. Well, the only force that's pulling it towards the centre is what we call the support force. So it is the support force in this case which is keeping the modules, the pods around the London Eye, moving in a circular motion. If that support force disappeared, then we're going to lose that pod and it's going to fly off in a straight line. Apart from the fact gravity is going to interfere with it at some point, but it's going to fly off in a straight line tangentially to that circle. And the last one we're going to consider, and we'll certainly come across more of this later on, is that when we have, so let's do a side-by-side view for a moment. There's a positive plate and there's a negative plate, and we fire in an electron, let's consider. Now let's look at it from the top. Then what you will actually find is that that electron will spiral round like that within the magnetic field. So what is it that causes the centripetal force of that electron in that field? Well, it is the B field. The magnetic field is causing the centripetal force in that case. So for examples, we've got tension, where the rubber bung is moving round in a circle and it's being kept in that circle by that tension force. If we cut the string, then that rubber bung will fly off in a straight direction. It will no longer carry on moving in a circular motion. we've got the Dragon capsule going around the Earth. Well, that Dragon capsule is being kept in orbit by the gravitational force. So if we remove that gravitational force, so we suddenly could turn off gravity, then that Dragon capsule would move on in a straight line and would go into the solar system. We've got the London Eye, and we've got the support forces holding those pods in place. If we broke one of those support forces, then that little pod would fly off tangentially at that point. And finally, the most complex one, we've got this idea of having a B field, a magnetic field, across two plates, look a little bit like that. Then we will see that the electron will spiral. So what is it that keeps that electron in a circular motion? And obviously you can see this is not uniform because it's either speeding up or slowing down as it gets closer, and I'll let you think about that one. But the B field itself is causing that centripetal force to allow the circular motion to take place. Okay, so we've looked at what's causing the centripetal force. We've looked at the centripetal acceleration and where it comes from. So let's go one step further and let's actually calculate our centripetal forces. Well, we know Newton's second law, one of the most important laws in physics, is F equals ma. And we know from what we did with the proof that A is equal to V squared over R, or in fact is equal to omega squared R. We've got two options there for our centripetal acceleration. So that means we're going to have two options for our force. So if A is V squared over R, then the force, the centripetal force in this case, is going to be m V squared over R. And the centripetal force, if we're considering angular velocity, is going to be F equals m omega squared times by R. So two more important equations that you really should know, which will now allow us to calculate the centripetal force that comes with our kind of calculation, our circular motion.